Here is a sequence of events that should be impossible. A shipment is marked as delivered before it was ever marked as dispatched. A payment is recorded as refunded before the original payment was processed. An employee's termination date is stored as earlier than their hire date. None of these are possible in the real world. In a database without temporal constraints, all three are perfectly valid inserts. The dates are stored, no errors are thrown. The impossible sequence sits in your data, looking identical to every legitimate record around it, until a report tries to calculate delivery time and returns a negative number, until a refund is processed against a payment that hasn't cleared, until payroll calculates tenure for an employee who appears to have left before they started. Temporal constraints are the rules that enforce time. Not just that a date is a valid date, but that events happen in the right order, that a start precedes an end, that a cause precedes its effect. Without them, your database accepts any sequence of events, regardless of whether that sequence is physically possible. In 2021, a logistics company's reporting system began producing delivery performance metrics that made no sense. A significant number of shipments were showing negative transit times, arriving before they were collected. The operations director questioned the data. The data team investigated. They found the cause quickly. The shipment tracking system had no temporal constraint between the collection date and the delivery date columns. Both accepted any valid date independently. Neither checked the relationship between them. During a bulk data import from a third-party carrier, date formatting differences between systems had caused collection and delivery dates to be swapped for roughly 4,000 records. The delivery date had been stored in the collection date column. The collection date had been stored in the delivery date column. The database accepted both. Neither value was an invalid date. Their relationship, delivery must be after collection, was never defined as a rule, so the rule was never applied. And 4,000 impossible records entered the system without a single rejection. The performance metrics had been wrong for 6 weeks before the operations director noticed. Decisions about carrier selection and route optimization had been made on those metrics. Some of those decisions were now being reversed. A single check constraint, delivery date must be greater than or equal to collection date, would have rejected every one of those 4,000 records at import. The import would have failed loudly. The bad data would have been corrected at source before it touched a single report. Temporal constraints come in 3 forms. The first is sequence constraints. These enforce that one date or timestamp must come before or after another within the same record. A hire date must be before a termination date. An order date must be before a shipment date. A session start must be before a session end. A contract start must be before a contract end. These are enforced with check constraints that compare 2 columns in the same row. The rule is simple to write. It is almost never written, because the sequence is so obvious to the people designing the table that they never think to tell the database. The obvious sequence is exactly what gets violated when data arrives from an external system, when a migration runs with unexpected formatting, when a developer inserts test data manually, or when an integration sends timestamps in the wrong time zone and the conversion produces a date that preceded the event it was supposed to follow. Obvious to humans, invisible to the database until the constraint makes it visible. The second form is dependency constraints. These enforce that one record cannot exist until another record it depends on already exists. An invoice cannot exist before the order it invoices. A shipment cannot be created before the order it fulfills. A review cannot be submitted before the purchase that entitles the reviewer. These are enforced through foreign keys combined with date comparisons. The shipment table references the order table. The shipment date cannot be earlier than the order date. The foreign key ensures the order exists. The date comparison ensures the order happened first. Both rules are needed. A foreign key alone says the order exists. It doesn't say the order existed before the shipment. In a system where data can be backdated, corrected, or imported, those are different guarantees. The third form is state transition constraints. These enforce that certain timestamps can only be set when the record is in the right state. A delivery timestamp can only be set when the shipment status is in transit. A cancellation timestamp can only be set when the order status is not already delivered. A published timestamp can only be set when the content status is approved. These are harder to enforce at the column level alone. They typically require either application-level enforcement, which as we have seen can be bypassed, or database triggers that run automatically when a value is inserted or updated. A trigger is a piece of logic attached to a table. It runs every time a specific operation occurs, every insert, every update, every delete. It cannot be bypassed by application code, by migration scripts, or by direct database writes. For state transition rules, a trigger is often the only way to enforce them reliably at the database level. It checks the current state before allowing the timestamp to be set. If the state is wrong, the operation is rejected. The impossible transition never occurs. Here is the failure that makes temporal constraints more urgent than many teams realize. Bad temporal data doesn't just produce wrong reports, it produces compounding errors. If a delivery appears to precede a collection, the transit time calculation is negative. Any report that averages transit times now has a negative value, pulling down the average. The average is wrong. Any threshold or alert based on that average is calibrated against wrong data. Decisions made against those thresholds are potentially wrong. If a refund appears to precede a payment, the cash flow calculation inverts for that transaction. Revenue for the period appears lower than it was. Costs appear higher. Any financial model that reads that data is working with a sequence of events that contradicts physical reality. Temporal errors don't stay contained. They flow downstream through every calculation that depends on the order of events being correct. And the order of events is something almost no calculation explicitly validates, it assumes. 2 practical steps for any database that holds time-ordered data. First, audit your date and timestamp columns in pairs. For every table with 2 date columns, ask whether a relationship between them should always hold. If the answer is yes, and no check constraint currently enforces it, that is a gap. Write the constraint. It is one line of the SQL. It will run on every insert and update from that moment forward for the lifetime of the table, at no cost beyond the moment of enforcement. Second, before any bulk import of historical data, validate the temporal sequences in the source data before loading it into the target database. External data sources have different timezone conventions, different date formatting standards, different definitions of when an event is recorded. Any of these differences can produce sequences that violate rules your database never thought to enforce, because the data that built it always arrived in the right order. The import that corrupted 6 weeks of logistics metrics was not malicious. It was a time zone difference between 2 systems that stored the same events with different timestamp conventions. The damage was 6 weeks and a set of carrier decisions made against metrics that were precisely, accurately, impossibly wrong. The real world has rules about time that no database enforces automatically. Causes precede effects. Starts precede ends. Collections precede deliveries. Hires precede terminations. These rules feel so fundamental that encoding them in a database seems unnecessary. Of course, a delivery comes after a collection. Everyone knows that. The database doesn't know it until you tell it. And the moment data arrives from a system that stored events in a different order, a different time zone, or a different column than you expected, the sequence that everyone knows becomes the sequence nobody checked.